So welcome back to Networking Fundamentals. And so let me just remind you of what you should have already learned. If you're coming into this thing, it's the first thing you've seen, let me encourage you. You have to go back and watch the initial pieces of this thing where we talked about the big network and talked about convergence and IP. We talked about the OSI model and the importance of understanding some of those concepts, because I'm going to tell you, we're going to dive in here in a few minutes. We're going to build a network, and we're going to really depend on us being able to speak the language of OSI. We talked about cloud and what the cloud does and how the cloud channel works. That was all things that you should already have under your belt at this point. So that today, in this session, we're going to build a network for Acme Corporation. You'll hear me refer to them as Acme Products. They're a products company, and they started their business in 1995, Joe and Susan. And so we're going to walk through our little scenario here with Joe and Susan. They start their business in 1995, and so Acme will have its own sort of timeline as we go through. There will be times when I have to say, okay, now things are like this, and I'll try to keep those straight in your head. But we're going to see this network, we're going to see computers and the computing system for Acme Corporation really develop over time. Joe and Susan, they start their business. They really do need to collaborate. And so Susan's the more marketing minded, and Joe's the more technical and sales minded. And so Joe's the technical one, and so Joe realizes that they need to connect their computers together so that they can collaborate. And so Joe creates for them the most simple network possible, which is with just a cable between these two computers. And it really does work that way. And so he puts a cable there. It's a special kind of a crossover cable. It allows them to communicate back and forth. And we've seen these network adapters in computers. You're right, you kind of know it when you see it. On the back of the computer, there's that port, that special port. And on the laptop computer, there's that network port, that Ethernet port, if you will. Now, why am I showing you all this? Probably something you already get. It's my excuse to talk about Ethernet. And so we need to talk about Ethernet for just a minute. There was a time when there were 3 competing network standards. There was something called ArcNet, there was Token Ring, there was Ethernet. All 3 competing technologies, all very different. And so Ethernet won, and ArcNet disappeared, and Token Ring disappeared. And so Ethernet was the one more popular. And so when we talk about Ethernet, we tend to talk in terms of speeds these days. You don't have to talk about, do you want Ethernet or not? It is ubiquitous. It is the standard. It's what every computer network uses to connect devices together. And so Ethernet simply has just come now down to a discussion of speed. And so we measure Ethernet speed in megabits per second, Mbps or MB/s you may see. And it refers just to network speed. And so today, desktop computers and desktop systems tend to run at 100 megabits per second, the most common speed, Ethernet speed for the desktop system. Now, Ethernet operates at layers 1 and 2. Okay, remember? We've talked about that postman, the postal deliverer. And so how he sort of functions at the level of managing what's actually written on the letter and managing that package of information, but also he has to have the feet in the bag and the ability to get where he's going to go. And so Ethernet does that. It's managing bits, just getting bits from point A to point B, but it's also involved a little bit in the frame and making sure the frame is whole. And so Ethernet operates at 10 megabits per second, 100 megabits per second, 1,000 megabits per second. Now, it started off at 10. The first iteration of Ethernet was 10 megabits per second, and originally it was called 10 base T. It's just a little phrase you may see, 10 megabits per second, baseband technology, twisted pair wiring, which we'll get to. 10 base T was 10 megabits. But along comes 100 megabits, right? There's always the need for speed. We always need our networks to run faster than they did before. And so along comes a 100 megabits per second version of Ethernet. It was so screaming fast, they called it fast Ethernet. If you ever see that term, fast Ethernet, it's referring to 100 megabits per second Ethernet. And so for a while there, it was called 10/100 base T because it was in transition. Lots and lots of 10 megabit per second devices that are now running on a network that's capable of 100 megabits. And so it had to be backward compatible, so to speak. And it was accommodating 10 megabit devices and 100 megabit devices at the same time. Now, for the most part, these days, 10 megabit per device is gone. And so most devices today will run at 100 megabits per second. Now, that's 100, fast Ethernet. Of course, give me more speed, times 10 gigabit Ethernet. Gigabit is 1,000 megabits per second. Very, very fast. And you'll see there's some reasons to have gigabit Ethernet, probably not so much at the desktop, but on what's called the backbone network. We'll come to that. And of course, give me more speed. Now there's a 10 gig Ethernet. Very, very fast for very special applications. Maybe we'll talk about some of those later. Ethernet runs on unshielded twisted pair, UTP, unshielded twisted pair. And so that's a UTP cable. I've just sort of split it open here. There's the connector, RJ45 if you're interested, that's what that's called. And here are 4 copper wires, twisted in pairs. There's a green pair, orange pair, blue pair, brown pair. And so that's unshielded twisted pair, and that's the primary transport mechanism for Ethernet. Now, it's copper. It's unshielded. That means that it doesn't have an electrical shield around the wires that protects it from all sorts of interferences. It's unshielded. And so as a result, that UTP cable has its limitations. And the primary limitation of UTP is its length. You can never have a UTP cable from one connector, the end device, all the way back to where it's plugged into the network. That wire can never exceed more than 100 meters of cable. Now, it's not magic, not a magic number. It fails at 101 and works at 99. It has all sorts of things to do with what that cable encounters between the end device and the switching device. And so unshielded twisted pair, though, and as a general rule, can only be 100 meters. So you may think, well, golly, how do we get around that? Excuse me. And the way we get around that is with fiber optic. Fiber optic cable is not electrical. It doesn't use copper. It uses light pipe, basically. And we've sort of seen what fiber optic does. It's a very fine, clear glass pipe, more like plastic because it's somewhat flexible. And so we have this end, and it communicates, instead of using electricity, it communicates using light. Electricity, voltage is either on or it's off, 1 or 0. Light is either on or off, 1 or 0. And so you can see, but the difference here is that we can get much faster bandwidths, much faster speeds with fiber optic, and much longer distances. So if you have to run Ethernet longer than 100 meters, then you may want to use fiber. Now, I'll warn you, fiber can be expensive. It's expensive to run. It's very expensive just to put that end on this thing. You actually have to polish the end of the light band here in order to make it work. Imagine polishing the end of one of your hairs. Very difficult. And so don't take this thing for granted. It can be a little troublesome and a little expensive. But it does give you options that UTP does not. So Joe convinces Susan that they need a printer. And instead of buying 2 printers, one for each computer, he's going to buy 1 printer. And while he's at it, he's going to add a file server. And we're going to connect up our little network using a little device called a hub. Now, Joe goes down to his local electronics store and buys this hub, a very simple little device. And he's going to connect now their devices. And I'm going to connect up my devices here so that you can kind of see how this goes. And so here's my laptop. I'm going to click that in place. We're going to plug that in here. Here's my phone in my example here. And I'm going to plug that in here. And I'm going to plug it into the hub. And you'll see, it's just about that simple. That's how we've made a little basic connection. That's how Joe makes his connection, using a very simple hub. Now listen, I talk about a hub. You probably couldn't buy a hub these days if you wanted to. But I'll mention it because it connects endpoints together. But it has shared bandwidth. Here's what that means. I want to introduce the term bandwidth here to you. Now, bandwidth is a term that we stole, a perfectly legitimate term that has a whole lot to do with radio frequencies and such. But we stole it from that, and we now have made it mean the speed of a data connection. And you might say, well, what is the bandwidth of this little switch? And you'll say it's 100 megabits per second. That's its bandwidth. It's just a term. It's a misnomer. And so we stole it, but that's what we're going to call it. And so bandwidth will be the speed of our data connection. And in our case here, it's 100 megabits. But the bandwidth on a hub like this, a very simple device, it's a shared bandwidth. Meaning that if it's 100 megabits for the switch, that each port now shares that 100 megabits. And if one of the users is using 60 megabits of the 100, there's only 40 to go around for the rest of them. And so that's a shared bandwidth. I just introduced that so we can talk about it later. It sends all packets to all the ports. It's a very simple device. It operates strictly at layer 1. This is a hardware connectivity kind of a device. This business is growing. You can see that Joe and Susan have added a couple of new employees, and immediately Joe sees that this little hub is not going to satisfy what they need. And so out comes the hub, and Joe goes and finds him a much more sophisticated device called a switch. And here's the switch he bought. He bought a pretty good one, as it turns out. And so here we have, now we're going to connect our devices up to our switch now. And so here we're going to connect in this phone. And then here, now here you may see 2 ports. 2 ports. One has an icon that has a little computer by it. One has an icon that has a little network beside it. So I would assume here that I plug this phone in to the network at the network port. But I wonder what that other port is. I wonder if I could plug my computer into that port. As it turns out I can't. And so what I have now is I have 2 devices running on one switch port. Now what does that make this phone? You know, it looks amazingly like a telephone to me. But what it makes this is actually a very small 2-port layer 2 switch. You can see. So it allows me to have the phone is acting like a switch, and I get 2 devices on one switch port here, which is interesting because now I haven't used a port here. I've got an extra port that I can plug another device in. So I'll bring another device into the network here. Here's a video surveillance camera that we'll bring into the network. There we go. And you can see now that I have 2 devices on one port. Now, for the sake of our discussion with Joe, and to keep this simple, what we're going to do is we're going to connect our computer back directly to the switch, just so you can see. Now, you're going to see that I'm going to use white cables to connect end devices to the network. So here we go. Here are our end devices. Great. Switch. We have to know what this switch is all about. Why did Joe bring in a switch? Well, he needed more ports. That was one sort of obvious thing. But a network switch connects endpoints together. Let me be more specific. A network switch connects endpoints to the network, right? And then ultimately they get connected together perhaps. And with a network switch like this, a more sophisticated product, it has distributed bandwidth. What that means is the bandwidth of this switch is 100 megabits, but now instead of being shared, each one of these ports, and there are 24 of them on this switch, each port has its own 100 megabits bandwidth. That's distributed bandwidth. Everybody has 100 megabits. Now, this switch builds a table of MAC addresses. Now, we should have learned some of that already. When we talked about OSI, we've talked about what MAC addresses are, how they relate. And so here's what the switch does. The switch, when it's plugged in, sends out a signal to all ports, and it says, hey, is anybody out there? And so this camera responds back, and it says, hey, here's my MAC address. And the switch doesn't care that it's a camera. He just takes the MAC address, puts it in a table, and says, okay, you're attached to port number 1. This MAC address, port number 1. The phone responds, here's my MAC address, and the switch adds it to the table and says, you're on port number 2. Computer says, here's my MAC address, port number 3. And the switch builds a table of MAC addresses, and it knows exactly where each MAC address lives. Remember, this is sort of like the address, the mailing address on the letter. That postal delivery guy has to know exactly where you live in order to deliver that, and the postal guy knows. So this switch builds a table of MAC addresses. That's a very simplistic way of describing it, but that's actually what happens. Now, the switch forwards packets, takes a packet of information, moves it along based on the MAC address, and the switch knows exactly where the MAC address lives. It's a layer 2 device. Switches are layer 2. Now, let's take a little side trip here for just a minute. And let me state some obvious things about power. Now, Every end device, every device that runs in a computer system, they're electronic devices, they require power to run. They require DC voltage. And the way that that this phone, for instance, traditionally might get power is a device like this. It's a power adapter. AC comes in here, DC comes out here. And you plug it into the phone or into the camera or into a wireless network access point, and they're powered up. But you may say, well, okay, that's fine. My computer sits at my desk. I can plug it into a wall outlet. I'm good. Even my telephone, I can plug it into the same wall outlet. I'm good. It sits at my desk, and that's all fine. But where do video surveillance cameras live? Right? They live up there. They live up high, and if you look around the ceiling in the room that you're in, you're going to discover there's no power outlets up there. Normally, they're down low around the walls, and so we could bring an electrician in, spend quite a bit of money, and have power outlets put upstairs where all of our video cameras are going to be. One more thing, think about where wireless access points live. They live up there too. Same exact problem. So what power over Ethernet allows us to do is to provide power over the Ethernet cable. And it only takes two pairs to provide the data connection. We have two pairs of wires left over. Why couldn't we just put DC power on one of those pairs? We can, and we do. That's what power over Ethernet is all about. And so PoE provides DC power over the Ethernet cable, which allows us now to eliminate the need for that DC adapter and for the AC power at the device. We get rid of the notion of that. We win three ways there. First of all, we don't have the expense of putting the power outlet up there, the electrician. Secondly, we don't have to pay the money that one of these things costs, so we've saved the cost of this thing times the number of access points or cameras or whatever it is. And now, this thing, when it's plugged into an outlet, sucks current the whole time. And so now we have a very green environment as well. And so there are three good reasons to use power over Ethernet. But here's the thing. The endpoint and the switch must be PoE compatible devices. I hope that's obvious. Is that for the switch to provide power to the end device, it's got to be a PoE switch. And the end device has to be PoE compatible. And so if you're going to attach a power over Ethernet device to a non-PoE switch, you think, well, how am I going to accomplish that? I have one of two choices. I can go back to my traditional power sources here, or introduce a thing called a midspan. And a midspan is a little box. You sit it on top of the switch. You plug the switch into the midspan, and the midspan goes out to the device. The midspan provides the power. The switch provides the switching. And that's the way it works. You may think, well, golly, why couldn't we just upgrade the switch? Good thought. So power over Ethernet is a great upgrade opportunity for the switching fabric of a network. So you can always introduce a midspan device if needed. Now let's talk for just a minute about PoE standards. We talk a lot about standards, a lot about protocols and the like. And so if we're going to get power to work appropriately, we needed a standard. And so we went to the IEEE Institute of Electrical and Electronic Engineers. And of course, they came up with a standard for PoE. They call it by a number, 802.3 AF. That's the name of the PoE standard. And 802.3 AF will provide a maximum of 15 watts of power. A maximum of. Now, if a device uses less than 15, that's fine. I'm sure they did a study that says, you guys who make devices that might run on Ethernet, how much power do you need? They were all below 15, and so they capped it at 15. That was the standard AF. But then along comes a video surveillance camera that has something called PTZ, pan, tilt, and zoom, right? And there's a motor in there that does the PTZ function, and it requires ultimately more than 15 watts. Big need here. We've got a lot of these newer cameras and other devices that are coming along that wanted more than 15 watts. And so I went back to the IEEE and said, we need a better standard. So they created a new one for them called 802.3 AT. And it's the newer standard. It's been around for a while now, to be honest with you. And so AT will provide anywhere from 25 to 60 watts based on how you implement it. Now we have two standards out there. And again, we're in one of those sort of transitional stages. Now, I doubt that we'll ever completely transition away from AF and to AT, kind of the way we have some of the others. The reason is it costs a good bit more to provide an AT solution. It's a much bigger heat sink in the back. And so, listen, I'm not the one to choose, but the fact is, for quite a while now, There may be AT products and AF products on the markets. In fact, some vendors, some manufacturers of switch products created power over Ethernet before there was the 802.3 AF standard. And we call those switches pre-standard switches. They were before the standard. And so they're older. And honestly, there's some adapters that would allow you to adapt the older switch to the newer AT. But again, think, it's an opportunity for upgrade at that point. When we're talking about power over Ethernet, you need to learn to ask some PoE questions. And the first one is, look, do you need PoE? If you're selling the end device, whatever it might be, if you're selling that end device, then your first question has to be, do you want PoE? Because you need to know whether I'm going to sell you the PoE version of the camera or the phone or the access point or not. Because it costs it's a little different product, a little different price. You're not going to sell the power adapter at that point. So do you need PoE? And if you do, yes, then are we talking AF or AT? So what am I selling? Am I selling you one of those, a standard camera or a standard phone? Okay, AT is fine. Maybe you have an AT switch. That's all good. If I'm selling you, I'm sorry, an AF. But if I'm selling you one of the newer cameras, one of those PTZ cameras that requires an AT standard, requires more than 15 watts of power, then it's got to plug into a switch that's 802.3 AT capable of the higher power. Do you need AF or AT? What are the power requirements of the endpoint? Do you need a midspan? If you're plugging it into a non-PoE switch, then you're going to need a midspan maybe. And how does that work? If you have some older equipment, maybe it's pre-standard, we need to take that into consideration. And keep in mind, upgrade, upgrade, upgrade. PoE is always a great opportunity to bring the whole network up to a current standard. That's power over Ethernet, a really critical kind of a discussion when we're selling endpoints along with the network. What should I know so far? What you should know so far is some things about Ethernet. We should know that at the desktop these days, it generally runs at 100 megabits per second, likely to for some time. That's pretty fast for desktop computers. There's some exceptions to that. People who need a lot of bandwidth, that's okay. But by far, 100 megabits per second is what endpoints are going to run at. There's also gigabit Ethernet, 1 gigabits per second. That's for a backbone network. We'll talk about that in a minute. There's also 10 gigabits, which is crazy faster, and there's some applications for that. We know that Ethernet runs on UTP, and that it has some limitations, less than 100 meters, and that it will run on fiber, and it has some limitations. It's costly, but it runs for more than 100 meters. That's what you should know about Ethernet. Power over Ethernet provides power to DC power to PoE devices, and there are two standards, AF and AT. Switches. What you should know about switches you probably already know, and that is they connect endpoints to the network, they forward packets based on the MAC address, and that's a layer 2 device. That's a network switch. Acme Products grows some more. So, Susan says, look, we have way too many people for that first floor office. I want to move my marketing department upstairs. And so, hey, Joe, make that happen. So great. So he buys some new computers, and he goes out and he gets him another switch, just like the first one, and introduces it into the network. And so now, one switch is on the first floor, one switch is on the second floor. He moves some of the equipment up to the second floor switch. But now, my first floor devices aren't connected to the second floor. How do I connect them together? And he connects them together with a switch-to-switch connection called an uplink port. Now, you're going to see I've used white cables for my end devices. I'm going to start to use blue cables for my network connections. And so what I do here is I'm going to know that my switch has, as a feature of the switch, something called an uplink port. And you'll see here are my regular 24 Ethernet ports over here. Over here you'll see some special ports. And so these are uplink ports. I'm going to connect my cable here to one of those and to the other one. And now my network is complete again. I have one bigger local area network that now accommodates all the devices. Now this is one way to connect devices together. It's one way, but it might be a short-sighted way, because what we might have done here is that we might have created a bottleneck, and that blue cable maybe is the bottleneck. So let's say a user on the first floor wants to access some big file up on the second floor file server, and so do some others. Then the bottleneck is going to slow down. The network slows way down. And the reason is because of that probably 100 megabit connection that we've made between the two switches here. Now, uplink ports are a feature of a switch. Very important to understand what they are and that they're critical to being able to connect our networks together. We've talked about Category 5, cable. We've talked about UTP a few times. And we understand that UTP has a natural limitation of less than 100 meters. And we get that. And so, we talk about Cat 5, you wonder, well, what about all the other categories? And there's a little chart for you on the screen there in your handout. Category 1 was where it all started. It was unshielded twisted pair, just like this, but it was for plain old telephone systems, POTS old phone systems. Very simple. IBM and Token Ring came along, and they allocated categories 2 and 4 to Token Ring cables. Do you know why Token Ring failed? It's because category 2 and 4 were crazy expensive cables. That's why, I think. Token Ring was probably a better technology than Ethernet. But Ethernet won out because they chose a very inexpensive cable. And the 10 megabits for Ethernet, they called category 3, Cat 3 cable. Of course, along comes 100 megabits. They tried to run 100 megabit cable, 100 megabit Ethernet on Cat 3 wire. Wouldn't work. It wasn't quite right. And so what they literally did was go back in and twist the cables a little more, a few more twists per inch, and you wound up with a better category of cable that could accommodate 100 megabits. And so, because 100 megabit Ethernet is the desktop standard, Cat 5 cable is the desktop standard these days. Along comes gigabit. We needed better. They twisted it more. We get Cat 5e, E for extended. I'm not sure why I didn't just go to 6, but I wasn't there. And so Cat 5e is gigabit Ethernet. Then they come up with Cat 6, which is really just a better version of Cat 5e. And then 6e is for 10 gigabits. You can actually run 10 gigabits on copper cable just like this. So there's Cat 5. And I'm limited to all sorts of things on Cat 5 here. But if I really had a problem with my bottleneck here, this blue cable has become a bottleneck, and I'm struggling. Do I have any options? And what I notice on the switch here is that there are some special ports. It's a special port called an SFP port. It stands for Small Form Factor Pluggable, SFP. And you'll see right beside the Ethernet port here, uplink ports, there are SFP. Now, if you look at that cable, you'll realize there are different kinds of connectors here, very dramatically different. This is a Cat 6e wire here between them. And I can now connect my switches together using those special ports, click those into place, and now I have a 10 gigabit connection between my switches, assuming the switch has 10 gig ports there. And so that's a very special kind of connection that now helps. It's one way that I can overcome that speed limitation that I was having here with my Ethernet. But alas, Joe doesn't have quite that much technical expertise, and he's still going to run with our copper connection. Speed limitation that I was having here with my Ethernet. But alas, Joe doesn't have quite that much technical expertise, and he's still going to run with our copper connection. Susan is frustrated with the slowness of her network, and she's struggling. She finally convinces Joe, look, Joe, I know you've done good, and I know you want to be the technical guy, but we need some help. And Joe finally breaks down, swallows his pride, and hires a pro. Joe gets a pro. He gets a professional network engineer, a company who can actually help him with the growth of this network, because this thing's really going to grow. This is a growing company. And so the network professional comes in and says, okay, Joe, I see what you've done, pretty good, but I'm going to make some suggestions to you about something we really need to do. What we need to do, the professional says, is we need to segment your network. We need to divide your one big local area network up into two smaller local area networks. And we're going to do that with a function of the switch called a VLAN, Virtual Local Area Network. And so we're going to take your upstairs switch and we're going to make it VLAN 1. And your downstairs switch will be VLAN 2. And now we can segment the traffic into pieces. That's what VLANs do. it's a function of the switch. The switch is a function that the switch performs. And you can separate your VLANs based on technology. You could have all of your video surveillance in a VLAN, and you can manage them separately. You have your wireless access in a VLAN, manage them separately. Or maybe you divide your VLANs up by department or something. Sales in one and marketing in another. That's the way Joe and Susan have done it. VLANs are a function of the switch, but VLANs are connected together not by a wire like this, but by something called a layer 3 switch. So let's introduce this thing. I warned you about the layer 3 switch, is that it would be a little complicated to understand, because immediately if you're thinking about what we learned before, wait a minute, I thought layer 3 was routers and that switches were layer 2. How can we have a layer 3 switch? Well, it's important. So what we have here, a layer 3 switch is a switch. It's a layer 2 device that can also function as a layer 3 device. And our switch here, what you see here is we have 8 ports. 4 of them we've configured in the switch to be a layer 3 switch. Layer 3 ports. These other 4 ports, they happen to be gigabit. This is a gigabit switch. And they happen to be, we're going to designate them as layer 2 ports. We have 4 layer 3 ports and 4 layer 2 ports on our layer 3 switch. So what we have here is a device that's functioning both ways. So we have to get rid of our cable, that cable there, and we're now going to connect our upstairs VLAN and our downstairs VLAN using the layer 3 switch. So we're going to plug in here to our uplink port and plug the other side into our layer 3 port. Then we'll connect our other VLAN exactly the same way and connect it up to the layer 3 switch. And now my 2 VLANs are connected together, as you can see. Now, a layer 3 switch, first of all, you know, and you've heard this before, that routers connect networks together. Routers connect networks together. And what I have here now are 2 networks. A VLAN is a network. And if I'm going to connect the 2 VLANs together, I have to have some routing functions. A layer 3 switch functions like a router to connect networks together, which means that it forwards packets based on the IP address, which also means now that every device in Susan and Joe's network now has to also have an IP address, not just a MAC address, but also an IP address to get them from one network to the other. And a layer 3 switch also functions as a layer 2 device. So it's a switch acting like a router. That's the layer 3 switch. Now, as an example here, if our VLAN 1 was on the first floor, but instead of the second floor, what if Susan's marketing department were up on the 22nd floor? Now, what problem do we have? The problem we have is that the UTP cable is no longer sufficient. It's going to take more than 100 meters of cable to get up there. So how do we do that? How do we get up to the 22nd floor? And the answer is fiber optic. And so we can pull the copper cable that connects the layer 3 switch up there and replace it with a fiber optic. So here's my fiber optic cable. Now I go to plug it in, but I have a problem. There's no place to plug in fiber optic into this thing. Remember SFP? So this is an SFP module for fiber. And so what I can do is I can plug my fiber optic into the SFP module, click it in there, and now my switches have an SFP module that I can plug into there. And I can connect now using fiber optic. Again, the reason for the SFP port. But Susan's not on the 22nd floor. She's on the 2nd floor. And so we're going to connect her appropriately. Layer 3 switch. Let's take a little sidetrack now and let's talk about storage. Now, you know, we're talking about networks here. This is all about networks and not so much about devices and solutions and applications. And storage, you may think of, as not part of the network. But we'll introduce storage here because it has implications to the network as we design it. So let me just teach you just a bit about storage. Now, this is representative of my storage device. And so storage, there are 3 different kinds of storage that you need to know about. One is called direct attached storage, DAS. And so inside of a server, and you'll see a server there in your picture connected to that, that backbone, or even the server that's up on in VLAN 1 or VLAN 2, those servers will have inside of them a hard drive, and that's storage for the network. And those servers now become application servers. They also become file servers. And so that's called direct attached storage. Very common, the most common implementation for really small businesses for sure. But there's another type of storage called NAS, network attached storage. Just like you think, it connects directly to the Ethernet. Now, what we want to do here is to make absolutely sure that we're not creating new bottlenecks. And so if we have a server here, a storage device, and everybody is storing their solutions, their products, their minute-by-minute orders to that device, and everybody's using it, then what we might wind up with is a bottleneck. And we just simply plug this device into any one of our ports here. We learned that lesson before. Now, so what we're going to do is we're going to connect our NAS storage device. There's our Ethernet port. We're going to connect it up to our gigabit layer 2 switch. These are gigabit ports. And so what we've created now is a gigabit backbone, a very fast backbone for our very fast devices, things like NAS and things like our heavy use servers. Put them on the gigabit backbone. And now they're all still connected to the 100 megabit. So any user who wants access to that storage has access across the network. But the storage device, which is heavily used, is not limited by slower bandwidth. We have maximum bandwidth here. And that's a gigabit backbone. And you see we've designed that into our network here. That's network attached storage. It has implications to how we design the network to start with. There's another device called storage area network, SAN, different kind of interface, faster, really kind of not relevant to our discussion, not relevant to network design as much as NAS is. One last thing, any of those cloud, server products can also live in the cloud. They can. Because remember we talked about the cloud. The cloud is not a matter of something, it's a matter of where it is. And so these IT storage devices can live on-prem, or these storage devices can live in the cloud. Just a little sidetrack on storage there. So what should I know so far as we build this network? We should know about switches, some new things about switches. We know that they're connected together by uplink ports. We know that a layer 3 switch functions at layers 2 and 3. We know about a VLAN is that it's a function of a switch and that it segments network traffic. It divides it up. And also VLANs are connected by a layer 3 switch. We should also know a few things about storage maybe. Here's what you should know is that it can be connected directly to the network, which means that we have network implications on how we design our network. It needs a fast connection, and so we might need a gigabit backbone in our network. And again, if you had a bunch of them or a lot of them, you might need 10 gig if you just needed the sort of state of the art. Of course, you have to make sure that your devices have a 10 gig Ethernet port as opposed to a 1 gig. And you'll know that storage, if it needs to, can live in the cloud.